Greetings, madam. This is our group assignment for engineering mathematics. This is our question 1. A rectangular electric burner plate of region 1 to 3 for the x-axis and negative pi over 4 to pi over 4 for the y-axis is heated up so that the temperature at point xy is equals to 10 open bracket 4x minus x square close bracket cos y. Find the temperature at the hottest and the coldest point on the electric burner plate. First and foremost, we should draw out the graph to get a clearer understanding of the question. Next, we should execute step 1, which is to determine all the partial derivatives of the function given. First, we shall find the partial derivative with respect to x and y. Next, we should find the second derivative with respect to x and y. And lastly, we should take the first derivative of x and differentiate it again with respect to y. Next, we should obtain the critical points of the graph. We can do this by taking the first derivative of x and y and making it equal to 0. From the equation of x, we get that x is equals to 2 and we get the coordinates of 2, 0. As for y, we get the coordinates of 4 and 0. Thus, we know that there are two critical points for this graph. As for step 2, we should compute all the partial derivatives using the critical points to be subbed into the determinant equation. Thus, for coordinates 2 and 0, we get the value of 800. And for the coordinates 4 and 0, we get the value of 0. We know that the second derivative of x is equals to negative 20, which is less than 0. Thus, with the value that we got for coordinates 2 and 0, which is 800, we know that this is a local maximum point. As for the coordinate 4 and 0, the value is 0. Thus, no conclusion can be made. Next, for the final step, we can use this coordinate to find the hottest point by substituting it into the main equation. Thus, we get 40 degrees Celsius. As for the coldest point, we know from the graph that the points 1 and negative pi over 4 and 3 and negative pi over 4 is the lowest points of the graph. Thus, substituting any one of these points into the main equation would give us the coldest point of the graph, which is also the lowest point of the graph. Now, I would pass it on to Dinesh and Musharraf.
Next, we'll be looking at question 2. A metal sheet of a polar region is given by the equation r equals to radius, angle r is between k and 1, and angle is between 0 and pi over 4. And r has a density function, sigma xy is equal to rho. Let k be in between of 0 and 1. This will be the angle for the polar region of the metal sheet. So the radius will be between k and 1, and k is going to be in between 0 and 1 as stated in the equation. For the angle, is stated that it is going to be between 0 and pi over 4. So we assume this is the angle since pi over 4 is equals to 45 degree. And this is the shaded region since the radius is somewhere in between k and 1, And so that's why we shaded this area in the first quadrant. So first we'll be looking at the Roman one, which is to calculate the mass. Next. So to calculate the mass is given by the equation double integral R double integral R sigma xy dA. And since mentioned previously, sigma xy is equals to rho. Next, we'll turn dA into a polar form, going to be r dr d theta. And then since dr is in the inside, we put the limit of dr, which is 1 and k in the inside, and then the limit of the angle on the outside, which is 0 and pi over 4. Since rho is a constant, we put it outside of the whole thing, so it will not interrupt with our calculation. So first thing first is we're going to integrate the inside part. So here the inside will be to integrate r. When we integrate r, we will get r square over 2 in the bracket with the limit 1 and k. So we substitute the limit and we will get 1 over 2 minus k square over 2. And since both denominators are the same, we can simplify the equation by writing 1 minus k square over 2. Next, we do the second integration. We'll integrate the angle and we will get 1 minus k square over 2 times theta in the bracket, and the outside will be the limit pi over 4 and 0. So the same as previous, we will substitute the angle and we will get 1 minus k square over 2 times pi over 4 minus 1 minus k square over 2 times 0. After we substituted the values, we will get the final answer, rho pi times 1 minus k square over 8. Then we move to question 2. I'll pass to Dinesh.
Okay, thank you, Moose. So now I'm going to explain the solution of center of mass of the metal sheet. So to find the center of mass, first we need to know the my and also mx, and also after that we have to find the center of mass of x position and also center of mass of y position. So the equation of x will be my over m, and the equation of y will be mx over m. So here my is the moment lamina about y-axis, and also the mx is the moment lamina about x-axis. So now we have to find the x. So first we have to find the my value. So my will be equals to double integral. There will be x, there will be rho, there will be r, dr, and also d theta. So dA will change to r, dr, and d theta, since it's a since we want it need to be in a polar form. And rho came from the sigma in bracket x and y, and also x here. And there's also limit of r, which is k and 1, and also there's also limit of theta, which is 0 and also pi over 4. Now the x will change into r cos theta, and the rho will taken out of the integral since it's a constant value. And now we have to times this both r, so we will get r square cos theta. Now we can integrate this r square cos theta. So if we integrate this r square cos theta by r, we will get r cube over 3 cos theta in bracket k and also 1, which is the limits. And we have to substitute the limits in the r, and the following solution will be 1 over 3 cos theta minus k cube over 3 cos theta. Now we can see here that cos theta, there's cos theta in both sides. So we can separate it from 1 over 3 and also k cube over 3. Okay. And 1 minus k cube over 3 will be taken outside of the integral because it is not involved in the second integration. The cos theta will be sine theta in bracket pi over 4 and also 0, which is the limits. We have to substitute the limits in the theta, and the following solution will be sine sine pi over 4 minus sine 0. So sine 0 is equals to 0 and sine pi over 4 is equals to square root 2 over 2. And the value of my will be square root 2 raw in bracket 1 minus k cube over 6. Now we do have the value of my and also the value of m from the previous question. So we have to substitute the my and also the m in the x equation. So my will be the numerator and also m will be the denominator. And finally, the value of x will be 4 square root 2 in bracket 1 minus k cube over 3 pi in bracket 1 minus k square. So now we do have the center of mass of x position. Now we have to find the center of mass of y position. To find the center of mass of y position, we need mx and also m. M we have found in the previous question. Now we have to find the mx. So mx will be equals to double integral y sigma xy r dr and also d theta. So this y will be r sine theta and sigma xy will be rho. So now we can take the rho and put outside of the integral since it plays as a constant value. And here the both r will be times and the value will be r square sine theta. Now we can integrate this r square sine theta. So the following solution will be r cubed over 3 sine theta in bracket k and 1, which is the limits of r. Now we have to substitute the limits into the r value. And the following step will be 1 over 3 sine theta and also minus k cube over 3 sine theta. Now we can see here there's sine theta on both sides. So we can separate it from the 1 over 3 and also negative k cube over 3. So the value will be sine theta in bracket 1 minus k cube over 3. So the 1 minus k cube over 3 will be taken outside of the integral since it is not involved in the second integration part. And sine theta will be integrated and will become negative cos theta in bracket pi over 4 and also 0. So we have to substitute the pi over 4 and also 0 in the theta. So the value will be negative cos pi over 4 plus cos 0. Cos 0 will be 1 and negative cos pi over 4 will be square root 2, negative square root 2 over 2. And the value of mx will be rho in bracket 1 minus k cube over 3 and another bracket 1 minus square root 2 over 2. Now we do have the value of mx and also m. So mx will be substitute in the y equation, and m also will be substituted in the y equation. And after substituting it, uh, the final answer will be 8 minus 4 square root 2 in bracket 1 minus a cube over 3 pi in bracket 1 minus k square. So now we do have the value of y, and also we do have the value of x, and we have to write in the coordinate form. Thus, the final answer will be 4 square root 2 in bracket 1 minus k cube over 3 pi in bracket 1 minus k square, comma 8 minus 4 square root 2 in bracket 1 minus k cube over 3 pi in bracket 1 minus k square. So this is the final answer for second Roman, for question of second Roman. So now I will pass to Kang. Thank you.
Right, thank you, Dinesh and Musharraf. Now we are going to move into question 3. Alright, so question 3 states that given a vector function, which is r in the terms of t, is equivalent to cos t times I plus sine t times j plus cos 2t times k. Right, so that is our vector function. Right, A, find the unit tangent vector. Alright, so we should know that the unit tangent vector, which is going to be t in the terms of small t, is equivalent to the derivative of the vector function over the magnitude of the derivative of the vector function. All right, so we are going to start with this part, which is our derivative of our vector function. All right, so for me, I'm going to separate into 3 parts because we got the coefficients. So basically, the coefficients in this vector function is for here. So we got here at I, which is going to be at cos t, at j will be sine t, and then at k will be cos 2t. So we need to derive each of these coefficient one by one. So we're going to be this one will be the cos t, and then another one will be cos sine t, another one will be cosine 2t. All right. So it will be easy for the I and j terms because we can just use the differentiation rules that is stated right here, which is going to be the differentiation of cos x will be equivalent to negative sine x, whereas the derivative of sine x will be equivalent to the cosine x. All right, so that is easy because we just need to change the terms from x to t. All right, so now let's look at the derivative of the k terms or the coefficients in the k. All right, in this setting, because it's going to be cos 2t, it's not going to be cos x or cos t or cos a. We need to use the chain rule formula. So in this, we let k, the derivative of v, will be equivalent to the derivative of k. All right, so we know that basically like that, we can say let u equals to t, and then let v equals to cos u. Okay, so we are going to start with derivating to t. So we know that actually t here is powered by 1. So following the derivative formula, it will be t minus 1 equals to 0, and then it will be equivalent to 1. So 2 times 1 equals to 2. So we are done with the derivative of u in respect of t. So now we are going to derive v in the respect of u, which is right here. And this one, we just need to follow the differentiation rules. Whereas for the different derivative of cos u in the terms of u. All right. So with that, we can get negative sine u. Okay. So with those in mind, and we also know that where u equals to 2t, we can just say that the derivative of v is equivalent to negative 2t. Great. So now it's because of chain rule. So we know that derivative of v in the terms of t will be equivalent to dv over du times du over dt. So it's shown right here. Okay, so we just need to times these two products, and the final answer we got for the derivative of k, the coefficient for k will be -2 sine 2t. All right, so here it's shown that the product we get of the derivative of the vector function. We can also simplify this as the coefficients, which is going to be here. So we can place this coefficient in front of I, and this one as the coefficient in front of J. This one is the coefficient in front of K. All right, so these are all the coefficients for I, J, and K. And with that, you can find the magnitude here, the magnitude of the derivative of the vector function by entering these coefficients for I, J, and K right here for each one of them. And with that, you just enter them, and then each one of them, because in order to find the magnitude, each of these coefficients need to be uh, squared, and the sum of it will be under square root. So the square root of the sum of each coefficient squared. All right. So with that in mind, here is the substitution. Right. So actually, looking at the trig identities of trigonometric functions, one of them are stating here at the first one is that apologies. All right, there we go. Sine to the power of 2x plus cosine square x is going to be equivalent to 1. So technically, we can simplify these two together, and they can be equivalent to 1 right here. So here we remaining the same, but also we can know that sine, actually one thing is that sine uh, square x can be equal to sine x sine times x. So we can rewrite sine square x equivalent to sine x times sine x, right? It's shown just right here. Okay, another thing, uh, but in this terms, it's not going to be t, it's going to be 2t. So imagine here is going to be 2x. So for each of them, actually, it's going to be sine square 2x equivalent to sine 2x times sine 2x. All right, look at here. Sine 2x can be rewritten in the trigonometry identities as 2 times sine x times cosine x. All right, but here in the terms of t. So here's one. So here's one, here's another one. Okay, so the product of this will be equivalent to 16 sine square t times cosine square t. All right, but it should be known that this can also be rewritten as here, right here. So sine square x can be equivalent to negative, 1 minus cosine square x. So, but here it will be in the terms of t. Oh yeah, my apologies. Actually, it should be the cosine x. So it'll be the square root of here. Should be this one. The square root of cosine square x is equivalent to 1 minus sine square x. All right. Okay. So with that in mind, we can write it down in the terms of t, replace it, or substituting it here, and then we just need to times this little term, and what we can get in the end is 1 plus 16 sine square t minus 16 sine power of 4 t. So this is our product of the magnitude of the first derivative of the vector function. Okay, so now we already have our derivative of our vector function, and we also have the magnitude of the derivative of the vector function r in the terms of t. All right, so here are the values, and we can just substitute them in right here. So it can be also be written as 1 over, this is the magnitude of the first derivative of the vector function times here the derivative of the vector function. So here after if we uh, expand it, this is what we'll get for I, J, and K in terms of I, J, and K. And we can also pull out the coefficients of I, J, and K. So here is I, now coefficient of I in the terms of in terms, but in front of I. And here is the coefficient in front of J. Here's the coefficient in front of K. So basically, this is our end answer of the unit tangent vector. So this is basically our end answer. Okay, so that is question 3A being solved. All right, now we are going to look into question 3B. So it says calculate the curvature, comment on the working method, and with a hint. This K can it's actually a Roman letter. It also can be pronounced as kappa, kappa, the curvature kappa. So it can be said on a more simplified form. Basically, the magnitude of the first derivative of the unit tangent vector over the magnitude of the first derivative of the function vector will be the product or the answer for the kappa or the curvature K. All right. But also it can be written as the magnitude of the first derivative of the cross product of the first derivative of the vector function or the function vector uh, and the second derivative of the function vector. Okay, so that is going to be the top, but it's going to be over the cube of the magnitude of the first derivative of the vector function. So basically, this is the formula we are going to use for question B, because if you want to use the first one, it will be a bit difficult. We might need to apply quotient rule because of these terms, the t's up at the dominant and the on the top and also at the bottom. So because of that, it'll be a little bit more tricky for us to find the kappa k, right? So now we know that here is our vector function. Okay, and we also found the first derivative of the vector function already. So with that, we can also find the second derivative. Okay, so it's going to be the same thing as question 3A, but this is going to be a second derivative for each of the coefficient. So for the coefficient I, here's for the I, J, and K. For I and J is going to be really simple. It's going to be basically using the differentiation rules. So basically the second derivation of negative sign in the terms of t will be equivalent to negative cos t, and the second derivation for cos t will be equivalent to negative sine t, right? Whereas for the derivation of k, which is the derivation of, the second derivation of k will be equivalent to the second derivation of negative 2 times sine 2t, right? This is going to be same as question 1 also, 3a. Why? Because we are going to be applying the chain rule formula, right? So it's going to be the same thing. So I'm going to go as this quicker. So at the end of this, we are going to be getting negative for cos 2t. All right. So here is basically what we found for the second derivative of the vector function or function vector, which is going to be equivalent to negative cosine t times I plus negative sine t times j plus negative 4 times cos 2t times k. So that's basically our second uh, derivative of the vector function, the function vector, right? So now, with that in mind, we can actually put out the coefficients for each. So negative sine t is going to be in front of I, and cos t will be in front of j, negative 2 sine 2t will be in front of k, and same goes to here, I, j, and k. So now we need to find the cost product of the first derivative of the vector function and the second derivative of the the second derivative of the vector function. All right, so we got the values. So we are going to find this in the terms of matrix. So we are going to be using matrix. We're going to pull in matrix. So the first terms on top will be going to be I, always be I, j, and k. And the first row is going to be our first derivative. So here is going to be our first derivative, but the coefficient, yeah? So here is going to be the second derivative of our vector function, okay? And then now we can find and based on the terms. So in the terms of I, j, and k. So when, for example, at this term of I, we are going to be looking out of those who are not in the rows or columns, here the rows and the columns of I, and when it's going to be j, it's not we are not going to look inside of the rows of and the columns of j, and same goes to k also. So we are going to look outside of the rows and columns that is related to I, or at the same rows or columns of I. When it's in the terms of I, it's going to be J in terms of J, and then K will be in terms of K. So this is our 2 by 2 matrix that we got in the end for I, J, and K. Great. So now with that, here you go, our 2 by 2 matrix. So in order to solve this, we need to have the help of the determinant for 2 by 2 matrix. So here, if A is equal to the matrix of A, B, C, D, 2 by 2, we can say that here A, we can solve it as A, D minus B, C. So here going to be A, B, C, D. Oh, sorry, D. All right. So here we are also going to be using the trigo identities. So looking at I, so A times donkey and then minus B times C. So look here, A times donkey, B times C. So this is the first product we are getting. So you can see here there's a cos 2t and also a sin 2t. So basically we can use the trig functions right here, the trig identities. Solve here, we can replace it with these trig identities, all right, here, and then we need to times it in, we need to expand it, so we can continue on. So now here we got a little issue, which is that the 8 sine square t and also negative 4 sine square t. So now we can also simplify, because we can see here is that actually these two terms are actually similar. See here, sine square t times cos t, sine square t times cos t. So 8 minus 4 will be equal to 4. So this is going to be what we getting. And then now we got a little issue, which is sine. So what if I want to turn every terms into cos? It will be easier, it will be more simplified. We can use this with the help of trig identities. So it can be seen here that sine square x is equivalent to 1 minus cos square x. So here we already replace it with the trig identity and then expand it. This is what we get. And because these two having the same thing, which is going to be cos t, we can just put them in, and then minus 4 plus 4 equals to 0. So what we got for I, the coefficient for I is negative 4 cos cube t. So this is going to be same for R, J, and K also. So basically here also A, donkey, B, C, here also A, donkey, B, C. So rinse and repeat. We also got for J is negative 4 sine cube t. It's going to be the same method that we use. Basically, we are going to be using the determinant of 2 times 2 matrix and also the help of identity trigonometric functions. All right, so now let's look at the last one, which is in terms of k. All right, what because sine square t plus cos square t. All right, that can be equivalent to 1. Why? Because at the first one here it says sine square x plus cos square x equals to 1. So here it will be equivalent to 1. So now we have found our product, the cross product of the first derivative of the vector function and the second derivative of the vector function. All right, so this is basically our cross product of the first the first derivative of the vector function and the second derivative of the vector function, right? So this is what we got. This is what's simplified. And that the question wants us to find the magnitude of the cross product here, the magnitude of the cross product of the first derivative of the vector function and the second derivative of the vector function, right? So we just need to pull out these coefficients of I, j, and k, which is going to be 1 for k, and then each of these components will be square, and the sum of it will be so basically the square root of the sum of each component square root. Sorry, not square root. It will be a cube. Sorry, not cube. It will be squared. All right. So this is what we get in the end for the magnitude of the first derivative. I mean the cross product of the first derivative and the second derivative of the vector function, right? So now we got that. So what we are missing now is basically the cube of the magnitude of the first derivative of the vector function. So here we already got the first derivative of the vector function. We just need to find its product. I mean that product. I mean the magnitude right here. We already got from question 3a. And now we just need to cube it. So here, it's a bit tricky, but looking at here at the law of surds and also its respective expressions. So the removal of root. So basically here it says that in another term you can say surd x will be equivalent to x power 1 over 2. Right, so this is basically for removal of root. So we can even rewritten this magnitude of the derivative of the vector function as 1 plus 16 sine square t minus 16 sine over 4 t 1 over 2. This is basically this having the same meaning as here. Okay, now we need to power of 3 or cube it. So if we cube it, so we know that, for example, am times an will be equivalent to am plus n, whereas am, power of am n, and then will be amn. There you go. So in this terms, it's going to be 1 plus 16 sine, square t minus 16 sine 4 power 4 t 3 over 2. Yeah, power of 3 over 2. So basically, this is our cube of the magnitude of the first derivative of the vector function. Okay, now we got what? We know that kappa is equivalent to the magnitude of the cross product of the first derivative of the vector function and the second derivative of the vector function over over the cube of the magnitude of the first derivative of the vector function. So we got both of these products already. We just need to substitute them into here, and this is an answer for the curvature K or the COPA, which is going to be surd, surd of 16 cos power 6t plus 16 times sine power 6t plus 1 over basically the power of uh 3 over 2 of 1 plus 16 sine square t minus 16 sine 4t. So basically this is going to be our answer for curvature of the vector function r in the terms of t. Here r in the terms of t cos t times I plus sine t times j plus cosine 2t times k. So basically that is all from me for question 3. I hope that Madam is able to understand, and thank you Madam for listening. So thank you very much. Thank you.